So we're here for lecture 13 of the course Proof Complexity as a Computational Lens. We are going to switch to space complexity and talk about what it means. In what sense do we measure how much memory a proof uses? And can we say anything about this measure? So before doing so, we'll look at another computational model, a very simple computational model where memory has been studied a lot, namely pebbling. So here's a graph, a directed acyclic graph. Our graphs are going to have fan-in too. There's going to be a unique sink always. I'm going to refer to that as Z. So any Z you see today is referring to the sink of whatever DAG we're talking about right now. Our goal, we're starting with an empty DAG. We want to end with a black pebble on the sink. We want to get there as quickly as possible, but also as... Sorry? Say again?
Sorry, we're just trying to change some settings here.
Are we okay?
Yes, we are perfectly.
You're okay. So we want to black pebble the sink, and we can do two things. We can place black pebble on V if V is empty, and if all the predecessors have pebbles on them. The immediate predecessors, okay? So in particular, if I have a source, so a vertex without incoming edges, then I can always pebble it because surely all immediate predecessors of A have pebbles on them. So I can also pebble B, I can also pebble C, and I can pebble D. That's the first rule. And now, note that for the first time, now I can actually pebble P, which I could not do before. Okay. And the second rule that we have is we can remove a black pebble at any time. So in particular, now I remove. So note that at this point in time, we have done 1, 2, 3, 4, 5 moves. And we have 5 pebbles. Now I'm removing 1 pebble, so now we only have 4. I'm going to place that pebble there, and then I'm going to remove this and place it there. Now I'm going to remove both of those. And I can place a pebble there, and a pebble there, and remove both pebbles, and now we're done. I have my black pebble, and just because I'm polite, let me clean up. Okay, so this was a pebbling of the sink. And it used space 5. The pebbling time was the number of moves, which I forget. That must have been the number of vertices times 2 minus 1, because I placed the pebble and removed the pebble everywhere, except I didn't remove it from the sink. Doesn't matter so much whether we count, for the time we could count either pebble placements or we could count both placements and removals. It's only a factor 2. It's sort of nice to say that something happens at every time step, so I'm going to count all the moves. So this was then a pebbling in time 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, probably 19. Okay, something like that. And this models the simplest type of deterministic computation you can think of, where there is no if statement. You're like given this is what you should compute, no if, no buts, just compute it. You can think of this as an arithmetic expression, for instance, and then you're sort of saying that the only way I can compute the result here, I need to know the result of the 2 operands before computing this result. So this is deterministic computation. Turns out that one model that is even more fun is non-deterministic computation. And then I can place a white pebble, which is a guess, on an empty vertex at any time. But this is a guess, so I need to verify it. So I can only remove a white pebble from V if the predecessors, the immediate predecessors, are covered with pebbles at this point in time. Okay? So now let's see if we can do some black-white pebbling of this graph. And my goal is now to see if I can beat 5, which is going to be interesting because my blackboard syndrome is terrible, but so far space 4. So far I think I only use space 4. Now let me do this, still only space 4. And now I realize that it would be kind of cool to just guess what this guy is. So let me guess. And now the rules say that clearly both predecessors of y are pebbled, so I can pebble y. And now I don't need this guy any longer, and it's black, so I can just remove it. Still 4. Pebble the sink. Now I clean up. Remove this one, remove this one. This one is a little bit, I can't just remove it, but I could just, maybe place a black pebble there. Maybe just for fun, I'll place a white pebble there. Can do that, right? The black pebble I can place because all predecessors are covered. White pebbles I don't need to justify. Now I can remove this because all predecessors are pebbled. This I can always remove, and this I can remove because all predecessors are pebbled. Does this make sense? So now we should write down like the formal definition. The space will be the max number of pebbles I used at any point. The time is the number of moves. I was planning to just do the definition by example. Are we happy with this? Okay, then we can just say some notation that I'm going to be using. I'm going to refer to the black-white pebbling price of a graph G as the smallest space of any complete black-white pebbling. Complete meaning start with an empty graph, end with a black on the sink, rest of the graph cleaned up. The black pebbling price is if I'm only using black pebbles. And I'm going to write pebble configurations. Like at time t, I say that my pebbling configuration, math BBP at time t, is going to be all the black pebbles at time t and the white pebbles at time t, where black t and white t are both vertices in the graph. This is just some notation that we're going to use. And without loss of generality, we're assuming that B and W doesn't intersect. There's a lot of slack in the exact definitions. One other thing that might become handy, I don't know, is I could also define a black pebbling or a black-white pebbling if you want. Start with an empty DAG, clean up the DAG afterwards. At some point, I will have placed a pebble on the sink. What's the difference? At most an additive 1. There can be a difference of an additive 1. The terminology that has sometimes been used is to say that you have a persistent pebbling if you like end with a black pebble there. If you just touch the sink along the way and then clean up and leave an empty graph, then we'll call that a visiting pebbling. But I don't think we'll need this distinction because we're only going to talk about asymptotics. So this game has been studied in a number of different contexts. I think one of the original motivations was for optimizing register allocation. It actually turns out that versions of this game are now all the rage if you're into cryptocurrencies and things like this. Won't go there today, but and also they're great fun. I spent most of my PhD thesis thinking about these games. They're a little bit addictive, so you should not start thinking about them unless you're ready to take the consequences. So one thing that we do know, and this is due to Hopcroft, Paul, and Valiant from 1977, is that for any constant fan-in DAG, where n is the number of vertices, as always, the black pebbling price is, okay, what do we know? Clearly, the pebbling price, the pebbling time is not so interesting. It's always going to be linear. But the pebbling space is at worst linear, but maybe could be better. I mean, here we you can sort of believe that the pebbling price here didn't seem to scale linearly with the graph size. It seemed more like it's scaling like square root something. Okay. And the question is, in general, can I always beat linear by how much? And the answer is yes, you can always beat linear by a log factor. This is assuming, again, that the graph has a constant fan-in. The big O depends a little bit on the fan-in. Let's fix the fan-in to 2. Then we know from Paul, Tarjan, and Saloni around the same time, and Gilbert and Tarjan, that this is in fact optimal. There exists a family of graphs, very explicit graphs, such that the pebbling price scales like n over log n. Oops, let me write this. This is even black-white pebbling. So there exists graph Gn with n vertices, such that the black-white pebbling price of Gn scales like n over log n. So this is typed. Okay, this concludes my quick overview of pebbling. We're going to get back to it later in the lectures. Questions on pebbling, or are we all happy with pebbling? You look very happy. So now we want to define space, not in this model, but we want to talk about resolution proofs. Today we're going to focus on resolution proofs. I'm going to try to give the definition in a general enough form that you will believe that we can extend it. Like when we're going to want to talk about space of polynomial calculus, space of cutting planes, it should be believable that we can do the same thing. We already had one definition of space before. Let me remind you about that, and let us change it a little bit just to make it slightly more convenient to work with. Suppose I have a refutation with 7 clauses. Let me just present to you the DAG structure. Here it is. And I commit to some linear topological sort. So this is like clause number 1, 2, 3. Apparently clauses number 1 and 2 are axioms, but then 3 is the resolvent of 1 and 2. 4 is again an axiom. 5 is the resolvent of 3 and 4. 6 appears to be the resolvent of 5 and 3, and then 7 is the resolvent of 6 and 2, something like this. So let me define the active clauses at a point in time. So the active clauses at time 6, okay, what are they? Well, that's going to be the current clause is always active. And then any clause that is a premise for a derivation rule of this line or anything that comes later is also active, because I need to keep it. You see that clearly at the time when I'm deriving this, 5 is active and 3 is active because they were used to get 6. 2 is also active because it's going to be used in the future. It was derived before, and I cannot throw it away because it's going to be used in the next time step. Note, however, that I'm done with 1 and I'm done with 4. Those are no longer in memory. So the concept of an active set is going to be, so if pi is a resolution derivation of the CL, let's say that the active set, math BBC or fancy style C at time t, consists of, well, the clause CT union all of the premises for clauses CJ, where J is strictly larger than T. All premises CI, I strictly smaller than t for lines cj, j greater or equal to. Does this make sense? So now I can define this is sort of the way to think about this, that if I'm presenting the proof to you, at all times, like if I have good board technique, then I'm only going to maintain this set. The setup is if I only have this set, and then you and I also know the CNF formula that we have written down on a slip of paper or something, then whenever I do a derivation, it's going to be applied on one of these clauses. So there's no reason for me to keep 1 and 4 on the board. Does this make sense? So now I can define for such an active set, we're going to be interested in 3 measures. The variable space, which is just look at all the variables. How many are they? That's the variable space. The clause space, which I'm just going to write space, somehow indicating that this is what I care most about. This is the number of clauses. In general, whenever we define space measure, the way to think about this is we're going to measure the same thing as size measures. Okay. So for cutting planes, we're also going to measure the number of lines. For polynomial calculus, however, actually, we're going to measure the number of monomials because that's what size measures. And then we have a third measure that is total space, and that is sort of variable space, but with repetition. So that's just going to be take all the clauses in my set and sum up all of their sizes, all of their bits. Are we making sense? And then now I can define the space of pi. That's just going to be for whatever of these variable space, clause space, total space. That's just going to be max over all the active sets in pi. Right? I just go over one by one, like here. I started space 0, space clause space 1, clause space 2, clause space 3. Now I'm down to clause space 2 probably, clause space 3. Here we have clause space 4. And then I guess here we have clause space 3 again. Something like this. So it seems that the clause space of this thingy would in fact be 4, and we accidentally happened to pick the configuration where the maximum was reached. And then the space for any of these 3 measures of refuting f, that's just the min over all refutations. Is this making sense? So it turns out that it's nicer to think about these active sets. So we're actually going to redefine resolution or any proof system you care about to have a configuration style derivation. So let me call this configuration style. Configuration style resolution. Now, a resolution refutation is a sequence of sets of clauses. I start with the empty set, and then things happen. And then when I reach the end, it's going to be the case that contradiction lives in there if I have a refutation. Okay. So the way you should think about this, I'm going to represent a resolution refutation as a sequence of active sets, if you will. So there are 3 rules that we have to get from CT minus 1 to CT. There is axiom download. Which is going to be that C sub t is C sub t minus 1 union an axiom in the formula. And we have inference where CT is CT minus 1 union sum D inferred from the clauses in CT minus 1. So I took two clauses from CT minus 1, I applied the resolution rule, I got some D, I can add it to myself. Note that in polynomial calculus, this is going to be now multiplication or linear combination or things like that. And in polynomial calculus, we could also download other axioms if we wish. And then we have erasure, which is just going to be that C sub T is a subset of the clauses I had before. And here we're also going to have, actually in some papers, in most of my papers, I think the rule is slightly more strict. I say that I remove exactly one clause. So I remove the clause C, where C lives in CT minus 1. Whenever it is convenient, I'm going to force you to erase the clauses one at a time. Whenever it is convenient, we can just sort of telescope and erase a bunch of clauses at the same time. Now I claim as an easy exercise that this is exactly the same definition as this active setting. So from now, whenever it is convenient for us, we're going to switch to configuration style. And we know that it is the same as if you listed your derivation as a sequence of constraints and defined space in this way. Are we happy with this? But then, and now you sort of, by accident, it turned out that we have the same notation for the active set. So now the space definitions are all the same. We are, by the way, you could also note that just as the other space measures, for instance, we could say, oh, I'm only interested in tree-like resolution derivations. And then I would get tree-like variable space, tree-like closed space, tree-like total space. We're going to look at general resolution. And we're going to care mostly about closed space. This is the most studied measure, most well-understood measure, and the measure that somehow people tended to care the most about. And it's also more fun because it turns out, we won't really have time to talk about this, but if you look at tree-like resolution refutations, for instance, it turns out that space is essentially just a logarithm of the length. So not too much happens. There's I think the Esteban and Toran have in their paper that introduced, so I should say this, that these definitions, these are not the original definitions, but there are two papers that one should be aware of. There's Esteban and Toran from 2001, and then there's Alekhnovich, Ben-Sasson, Razborov, and Vigderson from 2002. And I'm citing the journal versions. So Esteban and Toran, there are two earlier papers from 1999 by Esteban and Toran, and Alekhnovich et al. The conference version was in the year 2000, but they were all independent and mostly got the same results, except that Alekhnovich, Ben-Sasson, Razborov, and Vigderson also immediately generalized this to polynomial calculus and got some bounce there as well. Okay, so now are we happy with the definitions? Because then I think I'm going to get them out of the way. Now I want to, there's actually a third way of viewing a resolution derivation. Suppose I give you like a proof and I give you the diagram representation, and it looks something like this. Then you can say, okay, here's a proof. It has, there is some order in between these vertices, so the closed space is well defined. But I could re-optimize. I could just say, okay, do a proof of this form, but really, really optimize space. Now you realize if you look at these moves, it looks like you can always take an axiom at any time. So for instance, these you can always load into memory, but the only way you could load these into memory is if these two guys are already in memory. So you see now that sort of if I take the proof tag and perform a black pebbling of it, that will be a valid pebbling. And that will be a valid configuration style proof. Am I making sense? Okay. So then we can connect the two, and now you immediately realize the first observation, namely that if there is a refutation of F in length L, then what can I say about the space of refuting F, the closed space? Well, just, I have the graph, it has L nodes, and Hopcroft, Cole, and Valiant tell me that L over log L should be achievable. Right? Firstly, you can ask now, at what cost? This is something we're going to talk about later. We actually know for pebble games that to save this log factor, you might have to go to exponential time. Does the same thing hold for resolution? Is a natural question. And you can also ask, like, why did Hopcroft, Cole, and Valiant do this? Well, because they did it for the on-time versus space paper. Basically, their result that space is a more powerful complexity measure than time, in the sense that anything you do in time t, you can do in space t over log t. That's exactly this result. This is like their paper is a pebbling result. And for a long time, this was best known, and now I don't have the reference off the top of my head, but Ryan Williams has improved this to, I think, square root L. Right?
With a log factor as well.
Oh, there are some, okay, with some logs. Yes. So more or less like square root tilde L, something like this. Okay, and then you can, like, can resolution do this? Do this question make sense? Okay. So, and in general, like, what's the worst case measure? We have a good handle on worst case on space. That's kind of, worst case on with refutations. That's linear. That's kind of clear in the number of variables, because that's like, it's hard to get wider than that. For length, we didn't talk about it so much, but given what you know now, you know that exponential essentially 2 to the n is the worst case upper bound. What about closed space? Okay. So these are the type of questions that we want to talk about for like space lower bounds, trade-offs between proof length and proof space. It turns out that you can also, we'll talk today about trade-offs between width and space. We'll get there in a minute. And we'll also get to why. It turns out that I already had a spoiler alert that I think I told you a couple of lectures back that if you really want to understand closed space, turns out that width is a very good measure. Okay. So the first thing I want to prove is that take any CNF formula that is unsatisfiable, then the closed space of refuting it is at most the number of variables in F plus 2. And this is the first time you see it. I mean, space, you think of something as maybe in the polynomial regime, but it turns out that we can always get, space is never worse than the number of variables. And what is the proof for this? Well, okay, one thing I forgot to say. Also in this configuration style model, if you want weakening, you can have it, deriving a weaker clause. If you want, and then you can remove weakening, and you don't affect any of the space measures adversely. You don't increase width or length either. So sort of for all of these measures, if weakening helps you, throw it in, and then when you're done, remove it, and no space measure increases. Okay. So in particular, suppose I have a formula over 1, 2, 3 variables, because this is what I can fit here. I'll just do basically a decision tree. So branch over x1, true, false, x2, x3. And now I get 8 clauses. So this one will be labeled by, okay, I need to, sorry. So now I can label all of these, what am I doing? I can label all of these leaves by falsified clauses. So this is going to be x1 or x2 or x3. This one is going to be x1 or x2 or not x3 or not x3, etc. And here over here, just to be clear, right here I have not x1 or not x2 or not x3, and here I have not x1 or not x2 or x3. So you see that this particular path falsifies exactly this clause. Since the formula is unsatisfiable, for all of these clauses, there is a clause that is a subset of this. So just derive all of these by weakening, which you can do in just constant space. And now you realize that once you've done this, so I can always recover this clause in constant space when I want it. Okay? And now you just need to do a pebbling of this graph to show. I claim that if you have 3 variables, 1, 2, 3, then that's also the height of the tree. And I claim that you're going to pebble this graph in height of the tree plus 2. So first I start here. So height 1, I use 3 pebbles. Now keep that one there. And now I use 3 pebbles for this, plus I have to keep this one, so 4. And I max out, and now I can pebble this, right? And now by induction, I know I can pebble this in space 4, so keep this one here. I can pebble them both in space 5. And then pebble this. Okay, so just by induction, I get h plus 2 as the closed space. Okay, but this is the proof. Are you happy with this? So now I actually claim that we can say something slightly more interesting, that it immediately follows from this that the space of refuting any formula is at most the number of clauses in it plus 1. Okay, why? Let me prove a basic fact that you might or might not have seen. Because we're going to use this later also. So say that f is minimally unsatisfiable, if for all clauses C in f, if you take f and you remove C, you get something satisfiable. A formula is minimally unsatisfiable if it is unsatisfiable, but if you remove a single clause, then you can satisfy the rest. So here is, I hope, a minimally unsatisfiable formula, x or y, not y or z, and I think not x or z, and not z. How do I know this is unsatisfiable? Well, we just do a resolution proof, I guess. Resolve these two, so I derive x or z, and then resolve here, so I derive z, and then resolve with not z, and then we have contradiction. And now you just have to verify that if I remove any single clause, say I remove x or y, and now I said x false, y false, z false, and I can satisfy it. And then you have to check for all the others. Okay? So my claim is that if f is minimally unsatisfiable, then it has to contain more clauses than variables. It has to contain at least one more clause. This is tight, as you can see. We have 3 variables here and 4 clauses. For any n, you can get an unsatisfiable CNF formula over n variables with n plus 1 clauses. But there's no way n clauses can constrain n variables. Does the claim make sense? Okay. And note that if you're buying this claim, which we're doing our proofs pretty quickly today. So I'll hand wave this proof in a minute. I'll do most of it, but maybe a bit quickly. But note that immediately this gives this result. Why? Well, maybe f isn't minimally unsatisfiable, but then just remove a clause that you can remove. And just keep removing clauses until f is minimally unsatisfiable. Clearly, I can do this, yes? Okay, so clearly the number of variables didn't go up. So now I have an f prime over at most this many variables. That is refutable in number of variables in f prime plus 2. But I know that f prime contains at least number of variables plus 1 clauses. And this gives me this. Are we happy with this? So clause space is upper bounded by linear. How do we prove this? So we look at the clause variable incidence graphs. So here is the clause variable incidence graph, C1, C2, C3, C4, C5, and here are variables x1, x2, x3, x4, x5, maybe x6 also. And we need some edges, I guess. Maybe something like this. So these are variable occurring in clauses. Okay. So what does Hall's theorem tells me? For a graph G, a bipartite graph for left vertices U, right vertices V, it tells me that U prime in U has a matching into V if and only if for every U star that is a subset of U prime, it holds that the neighbors of U star on the right are at least as many as U star. Note that, as we all know, this is a necessary condition for a matching, because if there is a matching, then I can just take that matching and read off this, but it's also a sufficient condition. Okay. So now what we're going to do to prove, okay, what do we want to prove? We want to prove that a minimally unsatisfiable formula contains more variables than clauses. Okay? So let me start by taking a maximal S in F such that the neighborhood of S is actually strictly smaller than S. Okay, I claim that such a set must exist. Suppose it didn't. Suppose for all subset of clauses, the neighbors on the right were larger. Well, then I have a matching of all clauses to variables. So every variable gets to set a particular clause to the value it likes, and I have a satisfying assignment. Okay. So clearly there is no matching in this graph, because that would be a satisfiable formula, and it's unsatisfiable. So fix S. Suppose it's this set. Okay. So I'm going to argue that that's in fact impossible. So we need to argue that S is in fact all of F. And then clearly we're done. Yes? Okay. Why is that true? Note that X is the largest subset. So what can we say if I pick a subset of other guys, like maybe this subset or any other subset? I know I can't add that to S. Right? So any subset outside of orange actually has strictly more neighbors on the right than they are themselves. Because otherwise I would add it to S to get a larger set. So I'm satisfying this whole condition with some margin. Okay, so I actually have a matching from everything outside. So there exists a matching from F minus S to the variables of F minus the neighbors of S. Because otherwise S isn't maximal. So let's fix the matching. Maybe here it is. Now we're done. Why? Well, note that F is a minimally unsatisfiable formula. So this set is satisfiable by assumption. Otherwise, F isn't minimally unsatisfiable. What variables do I need to satisfy this set? Well, only these guys. What do I do about the others? Well, for them, I have a matching. So it turns out that the formula is satisfiable. Contradiction. Okay, so this now tells us that we have a somewhat of an understanding. So what can we say about space? We can say any non-trivial derivation, the way we define closed space, any non-trivial derivation has space at least 3. Why? Well, because you need to download 2 axioms and then you need to resolve them. And at that point in time, you're using space 3. Now, if you allow to resolve and erase at the same time, then you maybe would bring the space down to 2. We won't do that. Let's just be very picky about this. No immediate erasures, because that changes all the constants and then my notes will be messed up. But again, in the literature, you can allow sort of erasures could be a separate move or it could be done immediately after an inference. I'm going to have it as a separate move. And then the closed space, the minimal closed space is at least 3. We've seen that the maximal closed space is number of clauses plus 1. You never need more than that. At least if you only care about space, you could say, now you can ask, like, what can you tell me about the length of this derivation? Well, the proof we used to get it was exponentially long, right? We did basically a tree-like refutation. This is going to be exponential. So now you can see, like, can I achieve linear space without an exponential goal? Is a relevant question that we can ask. And we can also ask things like, so the whole game plays out between constant, at least 3, and linear. And now you can ask, like, what does it mean to be easy? What does it mean to be hard? Which formulas have constant space complexity or logarithmic? Or are there formulas that are maximally linearly hard? Is a natural question. Okay, and this was settled right away by ABRW. So Aleknovich, Ben-Sasson, Rasborum, and Victorson, and Esteban and Toran. Independent work, I guess Toran was the earliest studying this. So there exist families, in fact, 3 CNF formulas, if I want to say so, over big O of n variables and clauses. Actually, let me If I want to state it with this strength, let me also throw in Ben-Sasson and Dalmau 03 to be sure, because I think the first two papers don't get exactly these parameters. So let me throw in Ben-Sasson and Dalmau also. So linear number of variables and clauses, and the clause space in resolution of refuting Fn scales linearly. So worst case, like matching both of these asymptotically. Okay. How do these proofs? So we're not going to do these proofs, and you're going to see why in a second. Let me just talk a little bit how these proofs go, because this is going to be interesting later for us. Okay. And it's also historically very interesting because all of these papers did it in the same way, more or less. As always, there are like tweaks, and then with hindsight, you extract out like the common features. And here are the common features. I want to get a handle on the exact. So here is pi. I'm going to argue. We start out with the empty set. So I want to show, say, a clause space. Whenever I say space, I mean clause space today. Okay. So I want to show a space lower bound, strictly larger than S. Lowercase s will tend to be my clause space parameter. When you see an S floating around, that's clause space. Okay. So I want to prove that the clause space complexity of refuting F is strictly larger than S. By contraposition, look at any derivation, here we go, in clause space at most S. Okay. What do I want to show? I want to show that any such configuration is satisfiable. It does not contain contradiction. How would I prove this? It turns out that getting a handle on what these beasts look like is very, very hard. Or at least, I mean, I tried for several years. I was not able to do it. So we somehow need to simplify. And the way I'm going to simplify, I'm going to do the following, or Esteban, Toran, Aleknovich, and the others, and Ben-Sasson and Dalmau, do an inductive argument, constructing a partial truth value assignment rho, such that rho I is good for the configuration at time I. And rho is going to have two properties. Rho I is satisfying the configuration at time I. For reasons that will become clear, let me write this in a slightly funky way. I can write the following. There exists a 1 CNF formula that is satisfiable and is such that rho I implies CI. Is it just a slightly funky way of saying exactly the same thing? You know, what is it? What is a partial assignment? Well, it's the collection of the literals that it sets to true. How do I set a collection of literals to true? I just AND all of them together. That's a 1 CNF formula. Okay, so this is property 1. But now I somehow need to use the fact that I'm in low space. So what I'm going to maintain is I'm going to look at the domain of rho and say that that is at all times smaller than the space. Domain of rho I is smaller than the space of CI. Or, if you wish, if you view rho I as a CNF formula, the number of clauses in rho is smaller than the number of clauses in CI. Clearly, if I can do this, then I have a space lower bound. Are we buying this? How would you do this? By induction. Whenever I do an axiom download, let me just, we're not going to do this proofs, but sort of let me tell you how they go. Whenever I do an axiom download, Rho has set some variables here, a bunch of them, and now I need to argue that, I'm downloading maybe this guy, that I somehow need to find, a neighbor that is not in Rho. So now you realize that if this graph is an expander, and if I'm planning a little bit ahead, it's not just sufficient to be an expander. It could still be an expander, but I could have, I want to make sure if it's an expander that, for instance, I have not chosen all of the neighbors of C4. Right? How would I make sure to do that? Well, at all times, I find an assignment. Like whenever I do an axiom download, I find a free literal, I add it to Rho, and then I look at my residual graph, and I see now if something is going a little bit low, like is there some clause over here that has very few neighbors, then I ahead of time reserve a literal for that guy. Now this is very related to these supports and closures that we computed before. Essentially the same thing. I'm intentionally very, very vague here. But that's, so basically the axiom download step is going to work by induction. And since I'm adding a clause, I am allowed to add a literal. What do I do for inference? Nothing. The proof system is sound, right? So then I actually don't need to grow Rho even. So inference is the boring step. I don't need to do anything. What do I do for erasure? Note that that's a dangerous step, because I know that my Rho before certainly satisfied the erased configuration, but Rho is way too large. So what do I do? Well, I look at it and I realize that every clause that remains in the new C needs at most one literal. So let me prune Rho and just keep one literal per clause. So even though like the derivation might have done clever things with C and have compacted it in different ways, not too much. Not too much. So I'm just going to pick one literal per clause here that is already in Rho, and I'm going to shrink Rho correspondingly. If I can do this, I get my lower bound. We're getting a little bit ahead of ourselves, and note that I'm very heavily using this property of clauses now. You can think of, suppose we're going to be wanting to do exactly the same thing for polynomial calculus, and you're going to think about which of these steps crashes and burns for polynomial calculus, because it's going to crash and burn very bad. We'll get there in a few lectures. The interesting thing now is that when you do these proofs, you kind of already saw that we were looking at the closed variable incidence graph. We were arguing in terms of expansions. Have you guys seen this before? Like what kind of lower bounds did we establish via such methods? We established with lower bounds with such methods. So as these papers started to appearing, the funky thing was that it seemed in paper after paper that if you have a linear with lower bound for a formula F, you like stare at it, you take the proof, you shake it a little bit, you tighten the bolts a little bit, and you put the hammer on the side, and suddenly you have a closed space lower bound. As soon as you have a with lower bound, you do some extra work, you have a closed space lower bound. And pretty early on, people started saying, is this just a coincidence, or are these measures somehow the same? So that's what we want to talk about next. And I think we're going to talk a little bit more before we have a break. Maybe we're going to do our even, yeah, maybe we can do a result before the break. What did we do so far? We hand-waved the linear upper bound on closed space in terms of variables and clauses. We did somewhat properly the proof of the fact that a minimally unsatisfiable CNF formula contains more clauses than variables. This has been reproven several times in the literature. It is sometimes referred to as Tarski's lemma. And we have defined configuration style derivations. We have defined pebbling, and we have talked about in general how to prove closed-space lower bounds. Any questions at this point before we move on? Okay. So, interestingly, this question of whether closed space and width are the same, or at least actually what was written in the first conjecture that I think was appeared in several papers is width a lower bound on space? Is it the case that if I have a lower bound on width, that immediately gives me a lower bound on flow space? Note that this will have to depend to some extent on the, I mean, it's very easy to get a very strong lower bound on width. Namely, take a CNF formula with very wide clauses. And it's not so hard to find a CNF formula with very wide clauses that has a resolution refutation in minimal space 3. Like here's an example, x1 or x2 or xn is my first clause. And then you take and not x1 and not x2 and not xn. Okay. Clearly we have a linear with lower bound, nothing about space. So the quantity to look at, so if we're looking at the space of refuting f, what we should look at, we should compare that to the width of refuting f, say minus the initial width, right? Because otherwise we saw that otherwise we cannot get anything. Does this make sense? And then the conjecture that was phrased was whether something like this would happen. And this turns out to be super true. In fact, we can tighten this a little bit. What we are going to prove, I think, is this. And this is due to Atserias and Dalmau. The journal version is from 2008. The conference version, they proved it in 2003. So like from 1999 to 2003 there was a lot of development on space complexity. So this is what we want to prove. And the nice thing is, okay, there were a lot of attempts and people were trying and there were limited results, papers that I guess today are no longer cited. And it turned out that just out of the blue, Atserias and Dalmau realized that, of course, the right way to look at this, you shouldn't try to do proof complexity and like look at structural proofs or something like this. Obviously, you should look at finite model theory and Ehrenfurst-Frese games. What else? In particular, so-called spoiler duplicator games. And they give their presentation in terms of spoiler duplicator games. Which I'm not going to tell you what they are, except that we've had these games before, but we gave them another name because we talked to Pavel Pudlak. We should return to the prosecutor and the defendant. If you prefer your finite model theory and your Ehrenfurst-Frese games, and if I accidentally slip up later during the lecture, it might be good to know that prosecutor is the spoiler and duplicator is the defendant. And usually the way you play these Ehrenfurst-Frese games is you have two structures that, and you want to prove that they're different, but you have bound on your resources. And spoiler is claiming that it's blindingly obvious that these two structures are not isomorphic. And duplicator says, no, they're perfectly fine. Okay? And then they play a game where basically they look at these two structures and spoiler is trying to get duplicator to commit to, well, if they are isomorphic or if they are homomorphic, then where would you map this? Where would you map that? And then spoiler duplicator answers, I would map it here, I would map it there. And then, unfortunately, spoiler has a limit on memory, so spoiler cannot map too many elements at a time. And then you can measure like how deep the fact that this is in fact a non-isomorphism or non-homomorphism depends on how much memory the spoiler needs. What does this have to do with proof complexity? Well, the game that you're playing between the structures is basically you're playing between the prosecutor and the defendant are playing between a CNF formula and the true-false structure. And duplicator is saying that there's a nice way of mapping variables to true and false so that all clauses are satisfied, and spoiler is trying to generate partial truth value assignments that prove that this is false. And so what we're going to measure now in terms of prosecutor-defendant games, we're going to measure prosecutor memory. And prosecutor memory is, so we're not measuring now the number of records, we're measuring the size of the partial truth value assignment. So we're going to say that the prosecutor is limited to remembering p variables at any one given time. When the partial truth value assignment reaches size p, or maybe p plus 1, we'll see in a bit, then let's say k, and then I'm going to set k to p plus 1. That's the way we did it. So the prosecutor is going to remember k variable assignments, and then when you have a partial truth value assignment of size k, then you have to forget something. And then, of course, when prosecutor later asks defendant again, maybe defendant about the same variable, then defendant can answer whatever because there's no memory. And what I'm going to claim now, but probably not prove, but maybe it will be on a problem set, is if you believe, like we already talked about before, how the spoiler duplicator game, look, it happened already, how the prosecutor defendant game is actually just the resolution proof system in disguise. We already used this before. And now if you look at how this disguise works, it turns out that this memory that I talked about maps exactly to resolution refutation with, except possibly for an additive one. So let me write down the formal statement and then maybe a handbrake. Okay. So and in some sense it's interesting because this is already there in Pudlak's paper, except that I don't think he made any explicit remark about it and nobody else. And reading Atserias and Dalmau, it doesn't seem like they come from Pudlak's paper. It really seems that they come from their detour in finite model theory and are rediscovering Pudlak, as it were. And I should have checked before the lecture earlier and realized now I was actually curious whether Atserias and Dalmau even cites Pudlak's paper. Maybe this is something that we could check online during the lecture. I don't remember. So the theorem that we're going to use by Atserias and Dalmau, which is, as I said, you have to be a little bit careful because there's a setting of parameters where this breaks, and that in the original paper this is actually wrong. So I'm going to state it slightly more carefully. So suppose that F is an unsatisfiable CNF formula, and let P be strict. Let P be not strictly larger. Let it be greater or equal the initial width. So F is a PCNF formula. Then I claim that the following holds: that the width of refuting F is at most P if and only if prosecutor wins with memory at most P plus 1. Okay, so the way to think about this is that width W corresponds to memory W plus 1. Except that if the memory is exactly the initial width, then you don't know. Then you could have like an off by one issue. But we're never going to use it in that regime. And if you want this statement from Atserias, Dalmau, then the formal statement is that spoiler wins the existential P+1 pebble game. Okay. What's the existential P+1 pebble game? Well, the game is that spoiler places pebbles on things that should be mapped, and duplicator answers, oh, this map's there, this map's there. But it's like really, it's exactly the same thing. So, but if you're a finite model theorist, then you want to talk about spoiler and existential stuff. If you follow Pudlak, then you talk about prosecutor. Or actually, maybe Pavel Pudlak would also talk about spoilers, except he didn't do it in his proofs as games. And now I claim in one direction, let's ignore this plus P maybe, and let's just, something like this should hold, like in one direction. Suppose I give you a resolution refutation in width W. Then I claim it's obvious that prosecutor needs at most memory W+1. What will prosecutor do? Prosecutor will walk through the proof and will remember the current clause and will have a violating assignment of that clause. We'll start at the bottom at contradiction and walk through an axiom, maintaining the invariant that the current clause is falsified by the current record, right? So falsifying a clause requires at most domain size W, because that's the width. But then when you want to move to the next step, you might need one extra variable to ask about the resolution variable. So that's where the +1 comes from. And in the other direction, you just have to take an arbitrary prosecutor strategy that is winning and turn it into a resolution refutation and observe that this way. And the reason that you need this condition is this stupid thing that, well, as it is stated, if you don't have this bound on P, then you can see that, well, the spoiler actually wins this game with just one pebble. Or the prosecutor just asked about X, and then it's an immediate win. And if this theorem were true without restrictions, then this would mean that F would have a refutation in width 0, and that is not true. So that is why you have to be careful when the number of pebbles is like exactly that. Or the memory size is exactly the width. Am I making sense? Okay, so now I think we're actually at a point where we can maybe... But this means that in order to prove this, I can just do the following. I take a space-efficient proof. I turn it into a good prosecutor strategy. And a good prosecutor strategy is a low-width resolution refutation. Are you fine with this? Okay, but then we're done. I mean, because I will just, okay, so proof of this. Okay, take I configuration style. Prosecutor maintains the invariant that the current record row satisfies, let me call row I, it satisfies CI. Okay. If I can do this within my allotted budget, then note that this is absurd because this is contradiction. So somewhere along the way, I will win and I will catch the defendant cheating. Okay, so how will I do this? Well, whenever an erasure move comes, we just do what we did before, we shrink. Right? I mean, whenever I erase, I need at most 1 literal per clause. What do I do for inference? Well, nothing. Because if I have a row that satisfies the configuration and I derive something that is implicationally implied by the derivation, then that's implied. So the interesting thing is an axiom download. So suppose that so C sub t is equal to C sub t minus 1 union some axiom A, where A lives in the formula. So first, I claim that the number of clauses is at most S minus 2.
And if she have physical concerns, she will talk first to the director.
Okay.
Is that a question over there?
You should check. Yes. So for her, she will check any possible conflict of interest. It's not aware of, but she will check.
Oh.
She has a dynamic members or committees.
Mute. Okay. No questions so far? So why is this true without loss of generality? Well, because, not equal to, less equal, sorry about this. Because I need to download an axiom, then my memory goes up to S minus 1. Suppose I hit memory S, then I wouldn't be able to resolve or do anything. So my next step would be an erasure. But why would I download and then immediately erase? Then I just swap these two moves. Then I do the erasure first and then the download, and I will have a proof in smaller memory. Okay? So the domain size of row I minus 1 is at most S minus 2. And now what I'm going to do is I'm just going to ask about all variables in A. And note that I have to ask about all of them, and I have to remember all of them, because if I ask about the first one, and of course, defendant is going to say that no, that doesn't satisfy the clause. If I forget that and ask about the second one, then defendant will pretend that in fact it was that variable that satisfies the clause. So I actually have to remember all of the variables. How many are they? At most W, which is the initial width of the formula. And then when I've asked about all of them, either defendant violated the clause, but then we won. We're done. Or else I just remember that one literal and forget the other one. And now we're done. You just see that the width we got now that means that now we get that. What do we get? I think we wins that we get that prosecutor wins with memory. What is the memory? Now we have to be like super careful. I think the memory will be space minus 2 plus the initial width, and that is our p plus 1. So now we actually get that the width is this minus 2 plus this minus 1. And we're done. Yes. I have some more things to say about this, but I'm thinking that maybe this is actually a good time to take a break, because I think we will be reasonably fast. Well, a little bit. I think we're more than halfway through, so maybe this is a good place to stop. And again, I did this kind of quickly in the sense that we didn't write down like a formal full proof with all the details, but I'm not cheating you on anything. Like, if you take exactly this and you just write it down, then you have the proof. And this is also true for the linear upper bound on closed space, and this is also true for the size of minimally satisfiable formulas. The only thing I cheated you on is the n over log n lower bound for pebbling, and that's because it's hard. That's a non-trivial result that we don't have time to do. It would be wonderful to have, like, we could have a separate course on just pebbling. That's great fun, but that's not this course. So any questions now before we take a break? And let's take a break. Right after the break, so we're back from the break, and right before the break, we said that, well, for a CNF formula, in initial width W of F, closed space is an upper bound on width. So the refutation closed space is an upper bound on the refutation width, and you could think about this also for KCNF formulas. Then we can just forget about the initial width and say that except for additive constant, space is an upper bound on width. So in particular, note what this expression is. Refutation space -3, that measures the non-trivial space usage. We know that if you want to do anything in resolution, you're going to have to use space 3. So this is never going to be negative. But if the formula is at least somewhat hard, then you're going to have a positive number here. Okay. Similarly, on this side, well, if the formula is somewhat non-trivial, then the initial width, like, you're going to need to use all of the clauses in it, or at least most. So this is like a lower bound for refuting it. And then you say, okay, how much more do I need than, how much larger is the refutation width than the trivial lower bound, as it were? And then it said that the trivial width usage is upper bounded by trivial space usage. So this raises and now you immediately know, we also know that narrow proofs by necessity are short, right? So that an immediate corollary, if I take a formula, what can I say anything? Can we understand anything about constant space complexity formulas, constant closed space complexity formulas? And the answer is, well, if the closed space complexity is constant, then there has to be a polynomial refutation, a polynomial in the number of variables. Just because constant closed space implies constant width, and now we know that the width just goes up into the exponent. It's natural to ask if I could somehow have a more direct proof of that. Is there any way, if you just, if you didn't know about Atserias and Dalmau, but you know that this is true, how would you take a space-efficient proof and turn it into a short proof? And one question that you can also ask is, although I'm not sure how to formalize it, but you can ask, is there a direct proof of Atserias and Dalmau? I mean, we're talking about resolution refutations here. So there should be some way of massaging resolution refutations. What is this way? And I'm going to say something about this, but essentially a spoiler alert is that what I'm going to say is that, well, since the spoiler duplicator game, or the prosecutor defendant game, is just resolution in disguise, you are going to get something out of the proof just by running both sides through the translation. And we can do that, and we can look at it, and then you'll have to tell me if you're happy. I don't think you should be fully happy, but at least you can get something. One question that you could ask is, actually, do width and closed space coincide? If you look at the formulas in the literature, this was like up to, so what did we say? So closed space started getting studied in like 98, 99, somewhere around then, and then we had all these lower bound, then we had Atserias and Dalmau, And pretty much up to 2006, all we knew was, for all the formulas we care about, closed space and width coincide. So are they the same? So this is something that we will talk about in the course. And the answer is no, they're not. They're as different as could be. Almost. Like you can have constant width and almost linear closed space. But this requires a proof. And we'll maybe do this next lecture. This was my PhD thesis, basically. So this is how easily you can get a PhD. Also, you can relax this a little bit and say, suppose I have only a logarithmic closed space upper bound. Does that tell me anything about me? To the best of my knowledge, this is open. If I tell you that the closed space complexity is constant, that means that the length is polynomial. Can I achieve polynomial length and constant closed space complexity at the same time? Maybe with a blow up, not necessarily this bound, some bound, and not necessarily the same constant, but something. Can I get something simultaneously? To the best of my knowledge, this is open. It's not clear how hard this should be. If you're more on the applied side, why should you care about these kind of questions? Well, because closed space, and the reason why closed space is an interesting measure from a practical point of view is this is exactly how SAT solvers measure space. They keep track of the number of clauses they remember, and they're pretty aggressive about this. They're not measuring total memory usage, but they measure the number of clauses and erase clauses very aggressively. So if minimizing clause space can make bad things happen with other complexity measures, then maybe this is something that you want to know. Yeah, this is one reason to think about trade-offs. So I don't know if there's a direct proof here. Let me tell you one thing that you can do. Let me tell you what I know how to do, and then you'll have to tell me whether that's a direct proof. So let me attempt a direct proof, like in the sense of I'll take a small space refutation and I'll turn it into a small width refutation. Okay? So here is small space, closed space S. Here is the refutation, C0, C1. This is the empty set, C0, C1, C2, dot, 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 up to CT minus 1, C tau, which contains contradiction. This is in small space, closed space S. What I'm going to do now is take CI, view it as a CNF formula. I mean, it's a collection of clauses. That's a CNF formula, yes? Negate it and expand to CNF. You can do this. Let this be Vn. Are you with me so far? Okay. Now let me write pi prime to be d tau minus 1 dot 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 d2 d1 d0. What can you tell me about this? This, I claim, is the empty set. You take contradiction, you negate it, you write it as a CNF, you get nothing because you get vacuous truth. Okay, what happens if you take vacuous truth and negate it? It's contradicting. So far, it's looking pretty promising. Can you say anything about the width of these guys? Right? Because think about when you're taking, like if I have A or B, like I have A or B, and I don't know, not A or C, and maybe not B or E and you think about, now we negate this, then we're going to expand, we're going to say, okay, okay, so now I'm blanking on this. I think I need some help. We want to negate it. So we want it to be definitely, what are we going to do now? We're going to pick up with, okay, I think I need some help here.
Expanding.
Like we're going to pick up clauses like this is something that we're going to pick up. And what else are we going to pick up? We're going to have, well, not B or not C or not D, or also we're going to pick up basically all combinations saying that if one of this is false, because this is a way to satisfy the formula, right? I could satisfy A, I could satisfy C, I could satisfy E. And this clause says, no, you're not doing that. So for any way of picking out one of these, you're going to pick up one literal per clause. So in particular, the number of clauses is going to turn into the word. Yeah. So all you need to do now is to argue that you can patch this up to be a true resolution refutation. And you need some extra width here. How much are you going to get? What is it? You're gonna, I'm blanking now. What are you supposed to do? You get the initial width -3, something like this. It's like the extra budget you have to patch things up in between. So now, and unless I'm screwing up, which is very likely. And now just argue that you can do it. So actually, so sort of, if you have a space-efficient proof, take all configurations, negate them, and present them in reverse, and that's your small width proof. Is this a different proof, or is it the same proof?
Natural.
It's exactly the same, except that we, this is Filmus, Lauria, Miksha, Nordström, and Vinyals, I think, from 2014. So you could view it as a different proof, at least it got published, but I think we were fairly explicit that the way we discovered it is you basically, you take the Atserias and Dalmau proof and you run it through the prosecutor-defendant resolution correspondence, and then you get this. So there's one other question. We are not going to. Okay, so here's one question that you could ask also, which is somewhat related to one, I guess. But let me call this question number 4. Is can you minimize width and clause space at the same time? Simultaneously. So this we're going to answer no, hopefully next time. This turns out to be also no, and this is what we'll see now. So what are we going to see? We are going to see, let me maybe put it up here. Our goal is to prove that there exist 3 CNF formulas, Fn. They're going to be with a linear number of with linear and clauses and variables, such that the width of refuting Fn is constant. The clause space of refuting Fn is also constant. In fact, both constants are going to be 3. So like best you could hope for. But for any fix any refutation pi n of Fn, then for that refutation, if you measure space times width, you're going to get n over log n. Except for constant factors. Is the statement clear? So maximally easy with respect to width, maximally easy with respect to closed space, but pretty much hopeless to, except for a log factor. If you're optimizing one of the measures, then you see worst case behavior for the other. And it's actually, you could be, again, this is like, if you somehow manage to get the space down to square root n, then the width is going to be square root n over log n. So you have like a whole curve. Is the claim clear? Okay. What are these formulas? Finally, they're pebbling contradictions. So what are pebbling contradictions? Let me illustrate them by example. You fix any DAG of the type we talked about before, fan-in 2, although fan-in 2 is not too important, a unique sink, and then you write down a formula that basically encodes the pebble game, if you wish. Namely, for every source, we have a source axiom saying that, oh, every vertex I associate that with a variable. So I just overload. I mean, if you're really careful, you could write x sub a or something, but I'm lazy, so I'm just going to use the same name for the vertex and the associated variable. Okay, just out of laziness. So the source axioms say that all of these sources are true. So these are 4 unique clauses, 4 clauses of size 1. Then I have so-called pebbling axioms, and the pebbling axioms say that if both of my immediate predecessors are true, then I am true. So here we have that if A and B are both true, then P is true. This is this first clause. If B and C are both true, then Q is true. If C and D are both true, then R is true. If P and Q are both true, then X is true, etc. And it's a good thing to remember as a general thing that if you have like a set of variables X in some set V, and you have not X or some other variable Y, then this is just the way clauses write implications. This clause is actually just saying, if all X in V are true, then this implies Y. Right? This is nothing deep, but it's just a good thing to keep in mind when you see these clauses. So this is just pushing truth upwards, and then finally we have that, well, if X is true and Y is true, then Z also has to be true. So it's not so hard to see that so far, clearly this is going to force every vertex in the DAG to be true, except then we have a sink axiom that says, no, 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 the sink is false. So it's not so hard to see now. I claim what's the width? Well, the width is going to be the fan-in plus 1. We insist on fan-in true, so it's going to be a 3CNF. Number of clauses, number of variables, linear in the number of vertices in the graph. These formulas turn out to be amazingly useful. So they pop up all over the place. We're going to see them in several lectures in the rest of the course. So what can we say about these formulas? Well, they try to describe, they somehow encode pebble games. So it's interesting to see what pebble game properties carry over. The first easy thing is to say, well, if you have a black pebbling, P of the pebbling contradiction, what's my notation for this? I think I'm going to write this formula peb over G. Peb sub G. Peb parenthesis G is the black pebbling price. Peb subscript G, that's the formula. Okay. So suppose I have a black pebbling, then it's not so hard to see, as we talked about before, that you can just simulate that pebbling in resolution. Like whenever you place a pebble on a source, you can just download that axiom. Whenever I place a pebble somewhere in the middle, what do I know? So by induction, what I maintain the invariant that for all pebble vertices, I know that they're true. This is what my resolution refutation knows by induction. Okay. So now whenever, suppose I pebble X in my pebbling, then I know at that point that P and Q have black pebbles. So by my inductive construction, I know P and I know Q, and then I download the axiom not P or not Q or X, and I do 2 resolution steps, and now I derive X. Is this clear? Okay. And now you might worry a little bit that, well, in the end, what about the black pebble on Z? Well, then we derive that Z is true, and then we just have to do an extra step and download the sync axiom and resolve away, and then we have contradiction. Okay. So I claim that you should believe. So if there is a black pebbling P of G, then there exists a resolution refutation of peb G, where the length of pi is basically the time of the pebbling. Well, okay, I should have some big O's there. What's the width of this? 3, right? I'm just downloading pebbling axiom and then resolving away. So, and now what's my space? The space is the pebbling space. So the number of clauses is in fact the pebbling space. But I can say something, let me say something slightly stronger. I'd say even the total space. The total number of literals counted with repetitions is actually upper bounded by the space of P. Note that this in particular, total space is an upper bound on clause space. So this is a slightly sharper statement. Are you with me on this? We kind of, are you buying that we prove this between friends? There's a question?
Yeah, so when you have a constant width, sort of clause space and total space would be the same up to a constant anyway, right?
Yeah. Well, yeah. Yes. Yeah. Okay. Yeah. We're absolutely. So you're saying it's not like, yeah. You'll see why I insist on this later. But wait, yes, it's the same. I'm just sort of. I'm going to be a little bit careful now when I'm using total space, when I'm using clause space, when I'm using variable space. It's not going to be terribly important, except later it's going to be a little bit important, and then we're going to be happy that we did some proper bookkeeping. So here's another claim that is, okay, so this sort of tells you that anything a black pebbling can do, you can do in resolution. Now the interesting question is, what about the other direction? So this is Ben-Sasson in Palazzo and Wigderson. I mean, it's not exactly rocket science. They don't state all of this, I think, or if they state it in exactly this form, but this is probably the first time someone like wrote down that, look, these properties are true and they are very useful. Ben-Sasson and Wigderson also, okay, so maybe let me throw in Ben-Sasson and Wigderson 01, just because I think that's the first paper where sort of pebbling formulas were floating around in the sense that you take an interesting graph family and you generate this formula over the graph family. There are previous papers that do this. For instance, I think Raz McKenzie does this, 99. It's another paper that we'll talk about later in the course. Also some other papers. I think Ben-Sasson and Wigderson were the first who said, listen, like just, you know, there's the pebble game. There are arbitrary fanning 2 DAGs. You can always generate this formula. Let's give it a name. Okay, and then in a follow-up paper, they observed this, and that was useful. So Another not at all as obvious thing is the following. So it's around the same time. It's from 2002, but the journal version is from 2009. And this is the paper actually by, well, the way I should say, this is the paper that proves this. So what did Ben-Sasson do? He observed that actually so suppose, or if, is maybe, I'm stating my theorems a bit poorly today. For any, take any refutation pi of a pebbling formula over G. Okay, fix that refutation. Then, okay, let me write it slightly properly. From any refutation of the pebbling formula, we can extract a pebbling, a black-white pebbling. Let me give it a name, piece of pi, because it's extracted from pi. And the idea is that we're going to argue that kind of pi does the same thing as the resolution refutation does. What do I mean by this? So time of the pebbling is basically the length of the refutation, except for constant factors. The space of the pebbling is going to be big O of, and now I'm going to be super specific. I'm actually going to plug in variable space here. So note that variable space is arguably the smallest of the three measures. Well, it's not clear how variable space and closed space relate, but definitely this is smaller than, like you take the variables, you don't even count repetitions, and still the pebbling space is upper bounded by this. And we can actually say something slightly more precise here because we're going to use it later also. I'm going to say that the number of pebble placements is smaller equal big O of number of axiom downloads. So sort of this, I don't even care about your inference steps. Okay, is the statement clear? You give me you just sit down and do your refutation in whatever clever way you can, and then you give it to me. And basically what I'm going to tell you is like, you know what? You were just doing black-white pebbling in this time and this space. Or maybe you were doing something more stupid, in which case I'll sort of throw away parts of your refutation. But I can extract the pebbling with at least as good properties as your resolution refutation. So where time corresponds to length and space corresponds to variable space. But it's a black-white pebbling, not a black one. And we kind of know that it has to be a black-white pebbling. It has to be black-white. Wait, do we know this? I think we can probably extract this from one of my papers. Whenever did I write that? Maybe in 2012. Another very interesting question. So, okay, but then you can ask, but can we tighten this so that resolution can efficiently simulate any black-white pebbling? Yes? Good question. I don't know. That's a good question. One reason why we don't know this is that it's pretty hard to separate black and black-white pebbling. So I didn't say this, by the way, also that you notice that I saved at least the space of 1 here when we did black-white, yes? It's also not hard to show that for black pebbling, this is like something that I would give you on the problem set. It's like it's hard work, but it's doable. to say that actually the black pebbling price of a pyramid of this height, so the height here is 1, 2, 3. For height h, the black pebbling price is exactly h plus 2. It's not so hard to prove. You can ask, okay, in black, white, how much does non-determinism buy you? Turns out that most of factor 2. So there's a lower bound h over 2 plus constant, or plus minus constant. That proof is super complicated. So it would be a super nice question to. This is that is a paper by Maria Clave back in, I don't remember. I should have checked this. A single author paper anyway, on black white pebbling price of the pyramid, and it's a deep and painful paper. It's not clear why it's so hard. It would be really nice to clean this up to get a nicer proof, because pyramids, like pebbling formulas, show up all over the place. When they do, they often do so together with pyramid graphs because they're nice to work with. And it would be nice to have a very clean understanding of the black-white pebbling price in pyramids, and we don't. One other thing that we know is black pebbling price. I give you a graph, and I'm asking you, can you black pebble it in a space at most S? This is a p-space complete problem. This is a fairly deep result. It's non-obvious. What about black-white pebbling price? Open. Except there's a paper that says if you allow yourself unbounded fan-in, then you can get a p-space completeness result also for black-white, but that's kind of artificial. It's a little bit cheating. Is it like a really nice black-white pebbling, space, budget, S, prove that this is a p-space complete problem? Please do it. Okay? But if you want to do that, then in particular, that is one context in which it would be really nice to nail down the black-white pebbling price of pyramids exactly, because in the pebbling, in the p-space completeness result for black pebbling, the gadgets that you use pyramids all over the place, and then you use that you have an exact understanding of the pebbling price of these. Like, you do these gadget reductions, there's no slack, like you can't lose anything anywhere. And we just don't have, for instance, like one reason, not the only reason, but one reason why we don't have p-space completeness for black-white pebbling, we don't understand this graph well. I got a bit carried away. Where were I? Why did I start talking about this? Yes. Yeah, so and it turns out, so there's only a factor 2 difference, but like a lot of pain to prove that. And it turns out for most graphs in the literature, for some weird reason, it tends to be the case that black-white pebbling can save a factor 2. Like for family after family, you have access to non-determinism, you can save a factor 2. And you can ask, is this tight? And the answer is no. There are graphs for which it turns out that you can do them in black-white in the black-white pebbling game with space S, and black-only pebbling requires space S squared. This is known to be tight. It's never worse, like you never sacrifice, which is a little bit different from Turing machines, at least as far as we believe. So in the sense that the efficiency, like with well, actually, no, it's not. It's the same, I guess. Never mind. Anyway, so in terms of space, black-white pebbling can only save a square root space. We know that this is tight, but if you want to have a separation, S versus S squared, then the graphs are going to be gigantic in terms of this parameter S. It's another question, like give me polynomial size graph that exhibit an optimal separation between black and black-white pebbling price. Don't know how to do this. Lots of things that we don't know. And therefore, it's also not so easy to show, like in order to show that black pebbling, that resolution cannot simulate black-white pebbling, you'd have to come up with a graph family where black and black-white pebbling differ by more than a constant factor, and then you'd need to prove a space lower bound for this. And proving space lower bounds is not so easy. We'll see. Okay. Okay, so now what we want to do before we can call it a day is, again, we want to prove this, and I claim sort of, you've probably guessed it by now, that we want to use these formulas over these graphs. What graphs do we want? Well, maybe you kind of guessed it from this expression. We're going to use the optimally hard. We know that there are graphs we know that there are graphs that require n over log n, and those are the graphs that we're going to plug in. And there are explicit constructions. I'm not telling you about it, but anyway. Okay, so how am I going to show this? So it's not too bad. So firstly, let me just make an observation that for any resolution refutation, I'm interested in the total space of pi. And I claim that this is at most the clause space of pi times the width of pi. Okay, why is this? Well, because the total space of a configuration is summing up the clause width for all clauses in this configuration. So if I know that I never have more than this many clauses and every clause is at most this large, then any configuration has at most this many literals. So clearly that's an upper bound of the total space. Are you buying this? Okay, good. So then we prove this. This is our first observation. Then the second claim is that I want to prove. Okay, so what are, let's just say, so use GN for GN, the graphs in Paul, Tarja, and Saloni, 77, right? And Gilbert and Tarja, 78. So that's what we're going to do. And let's see what we can prove. I claim that clearly this holds. We have the width upper bound. We kind of argued that, right? This was this. There's just, I don't care about the space, right? I just do the bottom up. I download all the source axioms, and then I just resolve away. I never go above space. I never go above width 3. We're happy with this? Okay, good. And we did it. Slightly more interestingly, yes, this is what we have here. So let me make room for another less obvious claim. So the point is now that I need to give you a constant space, a refutation of these formulas, right? How am I going to do this? Any suggestions? So there are gestures from the audience suggesting some kind of top-down approach. We're so informal today. Should I do the proof by example? Like, are you happy if I can do it for this formula? That will convince you? If it's general enough. Okay. So I'm just gonna, let's start by downloading the sync axiom. And then I download X or Y or Z. And then I resolve. So now I have X or Y, both negated. So what I'm going to do is, spoiler alert, I'm going to derive, okay, my goal is to derive I'm going to derive in constant time clauses V is in WI, not V. This is what the clause is going to look like. And WI at all times is going to be a subset of all except I topmost vertices in the graph. Okay? Where topmost is with respect to some topological sort. I'm not sure if it's I or I minus 1, but we'll fix this somehow. So clearly, if I can do this, by the time I get to n, I have derived the empty clause. And I'm off to a good start. I started with this only contains the topmost, and now I'm done with the topmost. So from there now, I'm going to take the latest. So suppose I sort in this order. So first Z, and then every layer in this order. So then I should take Y next. So I have X or Y. And then I get, what do I get? Q or R or Y. And resolve. This will give me Q, not Q or not R or not X. Yes? And then I get rid of these. So space 3. Okay, now I should, okay, so where are we now? Now we have Q or R or X all negated, and I should take P, not P or not Q or X. And resolve. That removes X, and now I have not P or not Q or not R. So now you see I've gotten rid of X, Y, Z. It's kind of clear that it's going to continue this way, right? So after a while, like dot, 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 where will I get? Well, I will end up with a configuration that looks like not A, not B, or not C, or not D. Yes? Okay, but now I just download D and get rid of it and get not A or not B or not C. And then I continue. Now I have not A, not B, not C. As I have a source axiom for C, so I get rid of it. And now A or not B, and you sort of see where this is going with the download B. And now I have not A. And not A. I download the source axiom for A, and now I have contradiction. Clearly, I was only in space 3 all the time. This is a little bit neat, no? And now my board technique, I realized I have erased the theorem by Ben-Sasson that I needed, which is a little bit unfortunate. Oh, and this I should also not erase. Oops. My board technique is pretty terrible today, which is great when I'm lecturing on space. Okay, so now what can we say about any refutation? So fix any refutation in resolution of PEB-GN, where GN are these Paul Tardan-Saloni graphs. I know that, what do I know? Well, I know that the variable space of pi, Ben-Sasson tells me that this is upper bounded by the black-white pebbling price. Right? But this, we chose to be n over log n. Yes. And I claim that the variable space is definitely a lower bound of the total space. And the total space is definitely smaller than closed space of pi times width of pi. So that's the trick. So this tells us that whatever the reason that small space implies small width is, it might be a little bit complicated. Because it's definitely not the case that the same proof is optimizing these dimensions. So jumping ahead a little bit, I'm trying to check if there was anything I was going to tell you that I didn't tell you. But I don't think so. So one thing to think about while I'm checking whether I forgot to share any pearls of wisdom with you. So my plan is to use pebbling contradictions to actually separate space and width. And you can think about, what do you think about that plan? So we're going to prove next time, I think, that two things, that no width and closed space are not at all the same. There are formulas that are very, very hard for closed space, but are trivially easy for width. And there's only one problem with this. I mean, I want to use pebbling formula. But they are, if you look at it, like pebbling formulas are dead easy. Like again, algorithmically, what would happen if you give a pebbling formula to a SAT solver, for instance? Well, it would be solved immediately by unit propagation, right? The SAT solver wouldn't be enough time to start, because first it will say, oh, let me just propagate on clauses of size 1. And any pebbling formula is solved already during the propagation phase. So this is a little bit unfortunate. But they're so nice. I mean, they're so nice, you know, correspondences. And so our game plan is, and this is also something that, so what Ben-Sasson and Wigderson did, they actually thought one of the best separations between tree-like resolution and general resolution you also get by pebbling. And it kind of stands to reason, why would you get this? Like for a graph like this, you think about it, like when you're somewhere in the middle of the pyramid, you sort of need to use these guys in the middle a lot of times to make progress higher up in the graph. So it stands to reason that if you're limited to tree-like reasoning, and if you're doing like a bottom-up proof, then unless you can have these guys as lemmas, you're pretty much screwed. That's the intuition. The very unfortunate thing is that our top-down proof just broke all of this, right? So our question is, can we somehow make the top-down proof impossible? Can we forbid it? And what Ben-Sasson and Wigderson did for their separation is, oh, actually, now I'm blanking on this. The separation is probably in Ben-Sasson, in Palazzo, and Wigderson 04, by the way. So just to be clear, I think this is the paper that uses pebbling to separate. Again, you get formulas that have linear size resolution proofs, And the the tree-like resolution refutations have length or size 2 to the n over log n, where you guess where the n over log n come from. How do they do this? Well, they do the following. So we say for every vertex, we associate two variables, a1, a2, b1, b2, c1, c2, d1, d2. And we say that being pebbled is sort of that the OR is true. And now our formula is going to be something like a1 or a2, b1 or b2, c1 or c2, d1 or d2. Those are my source axioms. What are the pebbling axioms going to be? Well, they are going to be the, let's just do the first one. A1 or b1 or p1 or p2, a1 or b2 or p1 or p2, a2 or b1 or p1 or p2, one to go, a2 or b2 or p1 or p2. I'll have negations all over here. So for any vertex P with two immediate predecessor P and Q, we'll just pick up these four. And now it's sort of, what is this? This is just saying that A1 or A2 and B1 or B2 imply P1 or P2. Yes? So you do this everywhere, and then ... and then what do you do for the sink? Well, for the sink, you say, no, both of them are false. Okay? So now it turns out that now you can ask these correspondences between space and length and pebbling space and pebbling time. Note, before we had them for variable space, it would be really nice if we could get them for clause space instead. So that if I could say that basically my plan would be, my dream scenario would be now, look at any refutation, like I could still translate this in the same way, basically, in some way, to a pebbling, is my idea. And then I would like to say something like, oh, if the pebbling is in small time and in small pebbling space, the only way that is possible is because the resolution refutation had small length and small clause space. That would be on my dream scenario. Only problem is I'm not able to do this. So we won't look at these formulas next time. We know that if you take these formulas on binary trees, complete binary trees, then they inherit the same clause space complexity as in the pebbling game. You can go to pyramids and it still remains true. So you can generate these formulas over pyramids and the clause space complexity will be square root n. But this paper is even worse, is even more painful than Claude's paper. And then at pyramids we got stuck. So then it turns out what we'll talk about next time is, yeah, but do you insist on or do you allow me to use some other kind of substitution? And that's where Ben-Sasson came in and he said, Jakob, what about, is it okay with you if we try XOR instead? And then it turns out that for XOR and for many other Boolean functions that have similar properties to XOR, you can actually look at formulas like this, so-called generalized pebbling contradictions. And now you're going to be able to argue that with respect to length and clause space, these behave similarly as do the pebbling price. So again, what we're going to be able to prove is something like, you give me any refutation of a formula like this, and you're claiming that you were just refuting a syntactic object, the CNF formula. And I'm going to say, no way, no how, I'm going to extract a black-white pebbling that has the same parameters. And if we can do this, then the next thing we should do, then we're going to get space lower bounds because we're going to use Paul Tarjan-Solodi and Gilbert Tarjan. But we're going to get more than that, because suppose you get this tight a correspondence, Well, then there's a massive pebbling literature from the 70s and 80s and 90s that had lots of time-space trade-offs for pebbling. And then we can hope to just take them, and if these pebbling formulas preserve sort of the properties of the game, we should be able to translate all of these over to resolution and get just a vast collection of very strong time-space trade-offs, or length, clause space trade-offs for resolution, just in one fell swoop. That is the plan for next picture. Questions about today's material before we wrap up? Then I think we have deserved to be able to call it a day.